So if you've ever really craved a cheeseburger, maybe a steak, that first bite feels so satisfying. And most likely it's because your body was probably craving some protein, some iron, some zinc. The bacteria that are trying to spread diseases, they also get these cravings. And the worst ones, the worst pathogens, they don't just steal our iron. They steal it and then they dodge the antibiotics we use to fight them. That's where Dr. Jessica Sheldon comes in. She's studying the tricks drug-resistant pathogens use to steal iron. Dr. Jessica Sheldon's our guest today on Researchers Under the Scope. Hi, I'm your host, Jen Cannell, and today we are at the Health Sciences Building here at the University of Saskatchewan visiting Dr. Jessica Sheldon. We are looking at her research, which examines the microgenetics of some of the world's nastiest pathogens. These are the bacteria antibiotics can no longer kill. She's looking at ways we can effectively starve them out. Dr. Jessica Sheldon is an assistant professor of biochemistry, microbiology, and immunology, and she joins us now. Hello there, Jessica. Welcome to Researchers Under the Scope.
Hi, it's a pleasure to meet you, Jen.
What first sparked your interest in science and being a researcher?
I think that I was always a curious child, so I think science was always, in the genetics, so to speak. I think as we all do, I think I went through a phase where I wanted to be a marine biologist for a while. And then I thought I wanted to be an astrobiologist, which was a field that doesn't actually exist, or it didn't at the time. And then it actually was pop culture that informed my interest in joining science or becoming a scientist, because I came up in the era when the movie Outbreak was really popular.
I remember that one. That was really scary, though. And I had visions of that coming back during COVID. I'm like, is this it? Now, it looks like a pretty mild version, but Outbreak is kind of what changed your mindset.
Yeah, Outbreak and then another book called The Hot Zone. So two things that deal with pandemics, unfortunately.
And so from there, how did you start this out?
I did a high school placement initially, and it was in an immunology lab. And that was the first point where I was like, immunology is not for me, despite the fact that I'm now a professor in biochemistry, microbiology, and immunology.
Immunology, not your thing? This was just from the high school placement?
Just from the high school placement.
What happened?
So, cytokine cascades, pathways, just the signaling just got way over my head real fast.
What do you remember about just those early years?
So I'm not actually from an academic background. I didn't really know what I was doing. So I went into science because I was interested in it, and I developed a love of microbiology through my undergraduate courses. And I actually had no idea how to get into academia. It was one of my second-year microbiology teachers who said, I think you're kind of good at this. Maybe you should try it as a career. So from there, I ended up doing an honors project and moved on to graduate school.
What did you like about microbiology?
I'm just perpetually fascinated by the idea that something so small can change the course of history effectively. And we've seen that recently with COVID.
Yeah, definitely. And also even before that with the hospital spread bacteria that they're nasty, or soldiers who come back from a war zone and they've got a really gross one, Iraqibacter, I think they call it. Those are a couple of the ones you're looking at, aren't they?
The one that we're currently studying, Acinetobacter Baumannii, that was actually by design, my choice to study it. So I did my PhD in Staphylococcus aureus, or MRSA, or MRSA. That's a major hospital-acquired pathogen as well, but that field is very well researched. It's very well established, and I saw myself going into a faculty position, but I knew I needed to carve out a niche for myself where I would have room to grow, and really kind of a sandbox or playground of things to explore that really hadn't been looked at yet. With Acinetobacter Baumannii, I think I could see the writing on the wall. It was becoming extensively drug resistant at that point in time. So we can see with the silent pandemic of antimicrobial resistance that it was going to continue becoming more and more resistant over time. And that was going to be an area that we needed to research.
Can you take me back a little bit? Tell me about that silent pandemic. Like, why is this a concern?
It's because antimicrobial resistance has existed as long as we've had drugs, and even before that, because bacteria use antimicrobials to fight each other. So we've had this going on and we're running out of drugs, but there's really not a full appreciation for the fact that we're losing the ability to treat bacterial infections.
Oof. So in terms of your lab work right now and the questions you're trying to answer, what is the best way of sort of laying that out? Like, are there different streams happening in your lab, or is it one particular question you're looking at?
There's different streams. That was not by design. So the major focus of the lab in general is looking at emerging bacterial pathogens, specifically ones that are antimicrobially resistant. And for that, we're looking at, again, these nutritional factors that the bacteria require in order to survive in the host. And the overarching idea is that if we can block their ability to get these nutrients, then that's potentially a mechanism we can use to fight infection.
That's where my hugely oversimplistic cheeseburger steak analogy comes in. But they do get hungry, effectively. What are they hungry for?
One of the things that they're particularly hungry for, I guess, that my lab studies is nutrient metals or essential nutrient metals. So manganese, zinc, and iron are the main ones, and my lab predominantly focuses on iron.
What is your lab trying to figure out?
How they're getting iron, so the pathways or the mechanisms that they're using. And then ultimately the goal is, once we've identified those pathways, then there's two different mechanisms you can use to block it. So you can block it potentially using antibodies, which means the bacteria just can't take up the metals because the pathway's blocked. The other thing we can use is, it's a Trojan horse kind of philosophy or style. So what you do is, the bacteria have to take up iron. In that case, you conjugate this iron molecule or iron binding molecule to an antimicrobial or a drug, and then you trick the bacteria into taking up this drug antibiotic conjugate.
And you're trying to figure out, okay, is it better to block the eating altogether, or is it better to you can eat this, but it's poison? Is that kind of what's going on?
Yes, yeah. So basically they're transporters. The bacteria secrete these things, small metal binding molecules that are called siderophores. So they're released outside of the bacteria, they bind iron, and then the bacteria have these mechanisms to capture the siderophores and bring them back into the cell. So the idea is these mechanisms that they use to take these siderophores back in, you can either block it potentially using something like an antibody, or what we can do is trick the bacteria into taking up a drug by binding the siderophore to an antibiotic, and then effectively the bacteria will take it up thinking that it's getting a nutrient when in fact it's actually getting an antibiotic.
So if we were going to go down to your lab, what do we see actually when you walk in?
A lot of people pipetting small or moving small volumes of liquid from one tube to the other. What they're actually doing is generating genetic knockouts or gene knockouts in the bacteria. So we're blocking or disrupting those pathways for iron acquisition. And then we're looking at how that's impacting bacterial survival. So that gives us an indication of whether or not this pathway is actually essential for the bacteria to survive.
There is also a section of your lab looking at histamines, isn't there?
Yes, so that's kind of a complicated or not so complicated link. So there's some bacteria that secrete histamine. So we know that during gram-negative infective lung conditions, so things like pneumonia, that we see an elevation of histamine in the sputum of patients. And we know that the patients or individuals make histamine, and we know histamine in the context of allergy. Yeah. So since we know the host is making histamine, there's actually bacteria, mostly gram-negative bacteria, that, which is just a class of bacteria, that make histamine, and we don't know why. So one of the bacteria that we work on, Acinetobacter Baumannii, we know that these siderophore molecules I mentioned prior, they actually have histamine as an essential precursor to their synthesis. So we know the bacteria are using histamine in the synthesis of these molecules to get iron, but they're also secreting it into the environment. So we're not really sure why both the host and the pathogen in the context of infection would be making histamine.
And they're attaching it to their siderophores? those are like little scouts that go out and find what they need and then they pull them back in and, okay, give me that.
Yes.
Like little grocery shoppers for them. Okay. And what, in terms of like your lab and all the folks who are working in it, what has sort of been your overriding principle?
I think, well, I just can't say no. So since I was given my first opportunity by somebody that took a chance on me, not knowing how I'd turn out and with no background in science or academia outside of my undergrad, my philosophy has been to more or less give anyone that I can a chance, as long as they're showing some degree of enthusiasm. Well, I've like more than some degree of enthusiasm, a real enthusiasm for science and curiosity as well.
And what are you thinking you're going to be able to do, especially with these siderophores?
With the siderophores and the siderophore pathways, the hypothesis is that iron obviously is essential to the bacteria, and that if we block iron uptake pathways, then we can inhibit bacterial growth. And so that's behind the idea of drugs that we could develop in the future.
Are they like existing drugs, or these are drugs that we would have to develop that are basically specialized to be those Trojan horses?
So this comes back into the histamine story. If the bacteria are using histamine as this essential precursor to get iron, then we have this, again, a hypothesis that if we block the histamine uptake pathways using something like a pre-existing antihistamine, we could potentially inhibit infection or reduce infection.
Where did your interest in histamines come from?
That's another good question. So it comes both from academia and from a personal side of things. So I was actually diagnosed with a histamine metabolism disorder at the end of my PhD, and it happened to coincide right at the exact time I was starting my postdoc. And for the postdoc, I was given the opportunity to pick from a list of genes which gene in Acinetobacter Baumannii I wanted to focus on predominantly. And so there's this metal-regulated histidine decarboxylase, and a histidine decarboxylase is responsible for converting histidine to histamine. So I picked that just because at the time I had a real interest in histamine personally, and I had done my PhD in metal homeostasis or metabiology in Staphylococcus aureus, so it seemed like a logical leap to working in histamine and Acinetobacter Baumannii.
How did you manage to finish your PhD when you sound like you were pretty sick?
It was a trial, but at the time, what ended up happening is I went on an elimination diet to try and figure out what actually was causing me to produce excess amounts of histamine. So it wasn't the worst thing ever, because I lost a significant amount of weight towards the end of my PhD. But at the time, I was also more or less just writing, so it wasn't too bad.
Oh. Did you ever get to the bottom of it? Did you figure out what was making your body sick?
It's one of those things, kind of when you have inflammation, it's a cyclical situation where you make histamine and then you make more histamine. So I just take a lot of antihistamines at this point. Like
a crazy dose compared to the average, except for me. I'm the average one.
Yeah, several times what the normal dose would be.
Oh, heck. So, I know you are an early career researcher, and you've been incredibly successful in finding some grants. Can you walk us through usually how that works, and then what happened for you?
So I think the conventional wisdom is to apply for an NSERC grant first, which is a basic science grant, which is a smaller pot of money. And then once you have preliminary data, maybe in your second or third year, you apply for CHR, which is the larger health-based research grants. What I decided to do was to try and hit the sweet spot for CHR where you have a really good idea, you're really early on in, and you don't yet have a lot of preliminary data or publications for your lab. So I took a chance hoping to get some feedback, and I actually was lucky enough to get funded the first time around.
Congratulations. What does it let you do, that money?
So that really has allowed me to expand the lab quite quickly. So I have a fairly large lab for as junior as I am, but it really gave me the opportunity to give other people a chance on science too. So I've got several master's students and several undergrads at this point.
If your team in the lab does manage to come through with some of this work and you find answers, in terms of Acinetobacter Baumannii, what would that help us do in sort of a global picture?
In the global picture, we really need more drugs for Acinetobacter Baumannii. So in the midst of my postdoc, the World Health Organization actually declared it to be its number one priority critical pathogen outside of tuberculosis for the development of new drugs. So the idea is that we would develop or identify targets, potentially develop small molecules or antibody inhibitors to those, and then ultimately that would go into testing so that we eventually would have a new antibiotic to treat bacteria that at this point, in some cases, is pan-drug resistant, which means it's resistant to everything.
These are really smart bacteria.
They are, and also moderately terrifying.
What are the effects of this particular bacteria if it's left unchecked and it doesn't respond to anything in the body? What does it do to a person?
Unfortunately, if the person doesn't have a functioning immune system, it can be basically palliative care at that point in time. But it's important to note that this is not something that typically infects healthy individuals. Both Acinetobacter Baumannii and Morganella morganii, which is another pathogen we work on, both of them predominantly affect immunocompromised individuals.
So people who are already sick or in a hospital setting, or people who are already, their immune system is depressed.
Yeah, exactly. It would just give us another class of antibiotics. So there really hasn't been a lot of new antibiotic development in several decades. And the most recently approved novel class of antibiotics is actually these siderophore antibiotic conjugates. So there's a drug called cefiderocol, which is a drug that actually exploits siderophore uptake pathways in organisms like Acinetobacter, but again, it's developing resistance to that, so we need to develop supplementary therapies or alternative therapies.
Jess, this is really cool, and especially for anybody who's looking at those hospital-borne pathogens, it's really crucial. So thank you so much for your time on the podcast with us.
My pleasure, Jen.
Dr. Jessica Sheldon joined the University of Saskatchewan's College of Medicine 3 years ago. She's an assistant professor of biochemistry, microbiology, and immunology. Sheldon studies drug-resistant bacteria, their interactions with histamine, and the way they steal nutrients like iron to survive. We'll put a link to her work in our show notes, and you can find more at medicine.usask.ca. Researchers Under the Scope is a presentation of the Office of the Vice Dean of Research at the U of S College of Medicine. We record and produce this podcast on Treaty 6 territory. We pay our respect to the First Nations and Métis ancestors of this place. We reaffirm our relationship with one another. And we'd like to thank you for listening to Researchers Under the Scope and being part of it. I'm your host, Jen Cannell. Thanks for tuning in.